All right. So continuing on with buffers. So I want to, I went through a big overview of it. So now we're going to get into a little more of the specifics, specifically the shape of a titration curve and what's occurring along the titration curve. We have done all of the calculations that we need to do, including all of the relevant chemical reactions. But before we do that, we're going to start doing more and more review. And if you saw, I posted in the Google Classroom something called Thou Shall Not Forget. And it's a little bit of review, not a little bit, there's like 50 questions in each one. I think the one might even have more than that. But they're all short little questions like protons, neutrons, electrons. What is the gold foil experiment? All those little details that we need before the exam. So I'm just going to keep renewing those deadlines. Right now, I have it set so you could do it unlimited times. I saw a few of you tried it, didn't do so well, so try them again. And I added a second one. Right, I can only go ahead, I think, by 30 days because I have the free account. So if you want to try them, you can try them unlimited times. It's for you. Just do it. It will benefit you. You don't want to miss those tiny easy points that they put into the exam because you don't remember that an isotope involves, a different number of neutrons, things like that, like little simple things. All right, so related to that, you don't have to pay for anything review. I have tons and tons and tons of review stuff. If you do all of my review stuff, you will get a 5, if you understand, I promise you. My review is very, very focused on what is on the exam, nothing else. So right now we're at the point where I'm not covering anything that's not specifically asked on the exam. We have 2 tests left and then the exam, some review stuff in between. But this right here, I just Googled, this is even going back a few years, AP chemistry question of the day. There's several websites out there that will send you either to text or through email, however you want to get it, a question of the day. I put one of them here through Varsity Tutors. There is a pay version of this, but like I said, don't pay for anything. And it even has a timer. It has a link. You can email it to yourself. You can go to the home page. And this is the question of today. And then it talks about it down here. Some of the other subjects, if you want to add some of your other subjects. And then if there's a bunch of others, just Google AP chemistry question of the day and you'll find them. So hit pause for a second and try these 3. So these came the last 3 days when I signed up for one of them. All right, so I'm going to give you a chance. So hit pause and here come the answers. All right, so first one, a 5 milliliter sample of HF is titrated, so that's what we're doing, titrated with sodium hydroxide at the equivalence point. So I talked about the equivalence point yesterday, which is when the moles of acid equals the moles of base. Equivalence in terms of moles, that's what it is. So that means they're both limiting. So HF plus NaOH, these are both going to run out. Well, what's left over is the double replacement, but really this one is Na plus and F minus because of the net act. So these are all used up. So is the pH of Na plus, F minus, and H2O 7, greater than 7, less than 7, or equal to the pKa? And the answer is this doesn't affect the pH, but this does, and that's the conjugate base from the weak acid. So the pH will be greater than 7. Greater than 7. How do we calculate it? Well, then you add F minus to H2O and all of that. All right, so which of the following, when dissolved in an aqueous solution, would produce a solution that is basic? Well, that's an acid. Salt, 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 and salt. Na plus and Cl minus are both from strong, NaOH and HCl, so that's neutral. We're looking for one that's basic. NH4 plus and NO3 minus. This is the base from the strong acid. This is the acid from the weak base. So this is the one that affects the pH. So that would be acidic. K plus HSO4 minus. Strong base. Strong acid. That one's neutral as well. So it must be the last one. Well, what would make the last one? We have KOH and we have HF. Weak acid and its conjugate base. So that's why it is E. And the last one in the equilibrium reaction above. So we have H2PO4 minus plus H2O. So it's losing its other hydrogen and becoming HPO4 minus 2. In the above reaction, the chemicals that react as Bronsted-Lowry acids. Include the following. So we have acid-base pairs, essentially what we're doing here. Water acts as a base and accepts the hydrogen and becomes that acid H3O plus. That means this one acts as an acid because it gives up the H plus and it becomes the conjugate base. Now H2PO4 minus, I did mention this. I'm gonna say it again. My definition of 2 more O's than H's applies for the first ionization. This thing is already ionized. So even though there's 2 more O's than H's there, this is weak. It came from the acid PO4 minus. So we can't have a charge in it, in other words, when we're saying whether it's strong or weak, because this is a weak acid. A weak acid, when it ionizes, doesn't become a strong one all of a sudden, right? This is the conjugate base from that weak acid. All right, so to answer this question, we're looking for the acids. So the acids are H2PO4 and H3O plus. So just 2. This one's not, they're acting as bases. So the answer is 2 only in that case. All right, so that's our little review. So I want to jump right in now to the next page in our notes. But before we get there, I want to show you this. So unfortunately, this is the titration. I've gone through several generations of titration simulations to stop working. This is the latest one because it's Flash. The other ones were Java. We used those for years and years, and then it stopped with Java. Now they stopped with Flash. So this no longer works. There are some people working on it to try to make it HTML. And I did find another one, but I'm not sure if I want to subject you to it yet. It's a lot like doing a real lab. In other words, if you mess up, you got to start over. So it's a little bit frustrating. I'm trying to figure out the ways to make it a little easier for you. So if I figure that out, I'll let you do an online one. Otherwise, if you're hybrid, you may come in and do some titrations. Maybe I'll video you so you can show the frustrations to your virtual friends. All right, so essentially what we have, though, is a thing called a burette. So the burette, and we've used them, they have a tip at the end, there's a valve, and you can add drops very, very accurately by turning that on and off. So we fill it with a liquid. Now the liquid we fill it with has a known molarity, usually to 4 decimal places. So very, very accurate. The way you get it accurate, though, is you have to do a titration. So you do an experiment. You usually use a solid, so you could measure on a balance. That way you get 4 significant digits very accurately instead of trying to measure a liquid. So you put it on the balance, you measure, you dissolve it. So now you pull that over, you put it under, and you start adding drops until you see a color change. So the color change is, we use an indicator of some kind, an acid-base indicator that changes with pH. So we want to know when is the equivalence point. So the equivalence point, remember, is where the moles of acid equal the moles of base. So we want the pH to change, or the indicator to change color at a pH where the moles of acid are equal to the moles of base. That's the whole idea. Now that would be if we're going to do it in lab with an indicator, but I also have pH probe. So that's what this one is showing. So in the beginning, we filled the burette. You can see we added base, and the base we added was NaOH. So it's a strong base, and we know the concentration very, very accurately. I don't see it up here. Oh no, we know the acid in this one, but whatever. Let's say we know the base in this one. So now we put an unknown concentration, not an unknown acid, although they could say it has 1 proton, and then you know it's an unknown. But usually it's a known acid, but an unknown molarity. This one's doing it the opposite. So you know the molarity and you don't know the base, which is okay too. That's another way to do it. So then you start adding it, and you can see the pH started at about 2.73 because it's all acid, so it's an acidic. And then you start adding base, and the pH goes up. Remember, the color change occurs, but as it continues to spin, it'll go away. You keep adding base until you get a faint pink color that no longer disappears. Notice where the pH went up to. So the last one was added, we've added more base, and then it jumped up really quickly. And then it got really dark pink as we continued to add base. So this one would be past the equivalence point. So we wouldn't want to use this number if we were trying to do moles at the equivalence point. We want to use this one. So when we got to 18.22 milliliters of base added, by the time you got to 19.52, you could see the change got really, really dark. It got way past. And so we can then graph that. So this particular program, why I liked it was not only could you find the molarity along the way, you could see the color change when you got to the equivalence point, but also you could see the graph of pH. So that's what's on the y-axis. So 0 all the way up there, you can see up to 13 or so. And then down here is volume of milliliters of added of the base. This comes right from the Burette, the stuff that we're turning the valve and adding. So you can see it started out as an acid only. And then we started adding base, and the pH went up, but it didn't go up very fast. Why? Well, generally, this is a buffer zone. Now, this one wasn't a buffer zone because it was a strong acid and a strong base that I was talking about. But this particular one is the weak acid and the strong base. So we're going to talk about why that forms a buffer in a few seconds here. So all along the buffer zone here, we can use this equation, the Henderson-Hasselbalch equation. Notice what happened. You went at a very small amount of base, but the pH jumped from here all the way up to there. Well, at this midpoint right here, that's the equivalence point. So I guess this is a strong acid and a strong base. The way I know that is the pH is 7 at the equivalence point. So that's a strong acid and a strong base. If this was a strong acid and a weak acid and a strong base, then the pH would be somewhere above 7. So the equivalent, so this line would continue up to here, then it would shoot way up. It's always the midpoint of this vertical line is called the equivalence point. So let's look at some of that. So continuing now in our notes. So titration is a technique used in analytical chemistry to determine the concentration of an unknown acid or base. And you use that, as I said, by a known acid or base. You can do this as a pH indicator, which would do a color change, or we can directly read the pH as we add the base with a pH meter. And then as it does that big jump again, we know we're done. All right, so an example that I have down here then would be, what about if we have the strong acid HCl and the strong base NaOH? Well, it's going to give us this general shape when we do our titration and we graph pH versus volume added. Notice the pH right here, that equivalence point, we know that it's going to be 7. So we know the pH is 7 right here in this one because we have NaOH, which gives us Na+. We have HCl, which gives us Cl-. Well, neither of these affect pH. So when the moles of acid equal the moles of base, meaning they're both limiting, the only thing that affects the pH is water. So the pH is 7. All right, so let me zoom in here and let's show the reactions and show that we do already know how to do all of these pH reactions and calculations. Both reaction and calculation. All right, so at point A. So right now my points are a little off. So the point A I'm talking about is right there where you have 0, so there's no base, only acid. So the reaction is HCl plus H2O. Now, not equilibrium, it's a strong acid. H3O plus and Cl-. So we can directly measure the pH by measuring the H3O plus concentration, and that would be equal to whatever the concentration of the HCl is. Strong acid, 100% ion basis. All right, well, what about point B? I'm going to do point C first, then I'll talk about point B. So point C right here, we can now calculate the volume that was added to get this thing to the equivalence point. Remember, it's a steep vertical line. It's always the halfway point of that line is where the moles of acid equal the moles of base. So that would be here at point C. So point C, the reaction is HCl plus NaOH yields NaCl and H2O. Now these are limiting because by definition, they're all used up. They're equal. The moles of acid equal the moles of base, which means we have NaCl and we have H2O in order to do the pH at the equivalence point. Well, Na plus is the conjugate acid of the strong base. Cl minus is the conjugate base of the strong acid. So these don't affect pH. And so we have Kw equals 1 times 10 to the minus 14 and all of those equations that we All right, so what I want to point out is now if you take half of the volume, so that's what point B is supposed to be. It's called the half equivalence point. Now, the half equivalence point when you have a strong acid and a strong base is really not that relevant. It's more relevant when you have a buffer zone, but we need a weak acid or base in order to do that. So it doesn't apply in this particular one. We're going to see it in the next one. All right, so what's the reaction at point B? Well, we're still adding NaOH. So it's still the exact same reaction you have down here, H2O. But at this point, going from A until you get to the equivalence point, NaOH is the limiting all along that graph. So you're adding base, you're adding base, you're adding base, but you have to keep adding base until you get to the moles of acid that you originally started with. So all along here, you have less acid, less base than you do acid in terms of what was added. So how do we do the pH? Well, we have HCl, we have Na. This doesn't affect the pH. This doesn't affect the pH, but we're going to have some of this left over. And so HCl adds to water, and you get that same reaction we got right there. So once the NaOH is all used up, then you have HCl left over, and then you have the same reaction you had at point A. And so, again, a pretty easy calculation to get the pH. The molarity of the HCl is going to go down, though, because we're using up moles. So that's the hardest part of the calculation there, is figuring out how many moles of HCl you have left over. It's not that hard, though, because it's a 1-to-1 ratio. What about at point D? So now point D and point E, these are actually the same. These are past the equivalence point. So down here, as I said, the moles of acid are greater than the moles of the base. The moles of the base is going to be the limiting. It's going to be all used up, and you're going to have some moles of acid left over. Keep adding moles of base until the two are equal. But then you keep adding moles of base. Now the moles of base are greater than the moles of the acid. So now we have leftover OH minus. So the reaction for both of these is the same. It's a double replacement. None of these affect pH though, but now this one is the limiting, and you're going to have some of this left over. So now we get OH and then 14 minus to get the pH. So all of those calculations. So beyond the equivalence point, we now have NaOH left over. So that's the excess reactant. If you remember me showing and stressing stoichiometry and the ability to understand limiting reactants and excess reactants, how much is left over, and then the ability to calculate the molarity of that, that's what we're going to add a little bit, again, over the next few days. All right, so that is a strong acid with a strong base. What happens if we have the next one? More common ones you're going to see is a weak acid with a strong base, or a weak base with a strong acid. Now, a weak acid only partially dissociates. We understand that. The pH will rise normally at first, but as it reaches a zone where the solution seems to be buffered, the slope levels out. After this zone, the pH rises sharply, and then again, you get through the equivalence point. So this. Now, A should be here again. B is right there. C, and then D and E are beyond again. So notice the equivalence point this time is, so the pH of 7 is going to be somewhere around here. Because we have a weak acid, its conjugate base is going to affect the pH. So it's a basic salt that is produced at the equivalence point. So let's start at the beginning. So at point A, we only have the acid just like before. So we add it to water, we get an equilibrium this time, we get CH3COO minus, and we get H3O plus. So we have to do an ice chart. We have to use the Ka value, and we can find the pH. So pretty straightforward calculation there where we are calculating the pH of a weak acid all by itself. Now we start to add the base. So why is this a buffer in here? Well, at point B, let's say, or really anywhere between there, but let's say point B. So now we start adding base. So the reaction is, now technically it's again, a double replacement. I'm just going to leave off sodium. So sodium and hydrogen would switch partners. Remember, it's this hydrogen right here. It's this hydrogen right here that does the replacing with the sodium. So you get CH3COONA, but minus with the spectator ion, and then OH becomes H2O or HOH. So we have a buffer. Why do we have a buffer? So anywhere from point A all the way up to point C, remember, you have more acid than you do base, less base. So the base ends up being the limiting. So this ends up being the limiting. So that means you have some of this left over and you have some of this. So we can use pH equals the pKa plus the log of the base over the acid. Now there's a special point in here though, and that's called the half equivalence point. I said with strong acids and bases, you didn't really have to worry about that because, again, it's a strong acid or base. It's not weak. We don't have to deal with a buffer. There's no buffer. This one there is. So if we look at this equation, pH equals pKa plus the log of the base over the acid. Remember, you have more acid. Now, we're not talking about the OH minus base here. We're talking about the conjugate base. So we're comparing the ratio of the acid CH3COOH to its conjugate base CH3COO minus. So in the beginning, all along here, you have more of the acid than you do its conjugate. On the other side of the half equivalent point, now you have more of the base than you do the acid. So in other words, the ratio in here, base over acid, is either equal to 1, it's greater than 1, or it's less than 1. Well, here it would be less than 1. Here it would be greater than 1 because now you've passed the half equivalence point. But at the half equivalence point, that's what half equivalence means. At the equivalence, acid equals base. At the half equivalence, acid equals its conjugate base. Think of it this way. If I start with 1 mole, I don't have any of this or any of this, and I start adding base, eventually I'm going to get to the point where there's 0.5 moles left over. So if I add 0.5 moles of OH, it reacts with the 0.5 moles of the CH3COO. It's a 1-to-1 ratio, and there's 0.5 left over, excess reactant. There's none of this left because it's the limiter. But that means we made 0.5 moles of this and 0.5 moles of this. So if you notice, we have the same number of moles of acid and its conjugate base. So that would be where the base over the acid equals 1. Well, the log of 1 is 0. Check in your calculator. So the log of 1 is 0, which means at the half equivalence point, that's the whole special part of this. I'm just going to get rid of all of this. So at the half equivalence point, pH equals pKa. That's the special condition of the half. And if you can find it always, it's however many volume you added to the base, take half of it. So it's the half of the volume that you added at the equivalence point, or look at it this way, if you've added halfway to get there. So at pH equals pKa. Why? Well, because the conjugate base and the weak acid it came from, the ratio of the two is 1. In other words, they have the same number of moles. What about at the equivalence point? Now at the equivalence point, so the definition of the equivalence point, too many C's in there, is, get a spectator. So we're donating the hydrogen, we get not H0 plus H2O. And we get CH3COO minus NaH2O. Now the Na is there, but the Na doesn't affect the pH, spectator. They do sometimes ask what ions are there. It is there, it's just it doesn't affect the pH. So now this is the limiting and this is the limiting. When the moles of acid equal the moles of base, it's a 1-to-1 ratio, so that means they're both limiting. So you don't have either of those at the equivalence point, point C. So what do you have? We have CH3OO, we have Na plus, and we have H2O. Which one affects the pH? It's the weak conjugate. So the weak acid's conjugate base, CH3COO minus. So now we would have to do a hydrolysis calculation. So now we take that CH3COO minus, we add it to water, we do an equilibrium, we get OH minus because we're donating, and we get CH3COOH. You're going to have the Ka for the acid, but we need the Kb because it's OH minus. So all of those calculations, again, that we've been practicing. Once you get beyond the equivalence point, just like before, so these last two reactions would be the same. Now you have NaOH left over and all of the CH3COOHs used up. So there's zero amount of that left over. It's the limiting. There's excess left over. So we're going to find the POH again and 14 minus to get the pH. So we're going to try some of these calculations. As I said, there's lots of questions we're going to do over the next few days, including some for today. What about if we have a polyprotic acid, though? So when you have one like H2SO4, that has two hydrogens to give. Well, I said it always does it one at a time. So the first one is going to be HSO4 minus and H2O. And then HSO4 minus will do the second ionization energy. How do you tell what it looks like when you're doing a graph? Well, instead of having one equivalence point, then you're going to have two. So this demonstrates citric acid. Citric acid has a funky organic chemistry formula, but they would tell you that it is, diprotic. So it looks like it would be triprotic based on the formula. But so that's saying actually, sorry, that one is a diprotic one showing. If it was triprotic, you'd have a third. I thought they were showing. So we have, the first equivalence point. We have the second equivalence point. Now, what that also means is we have a first Ka, pKa or Ka, and then we have a second. So there's a first ionization energy, Ka1, and then there's a Ka2 on this one, diprotic. Losing the first one, then losing the second one. All right, so we're going to try some of these. So like I said, try that worksheet out that I posted for today, and let me know if you have any questions.